Okay, hello. So my name's Anton. I work at Plymouth University in the UK. Let me start by telling you a little bit about myself and our group. So we are currently 3 members of staff, 1 postdoc, 2 PhD students. I say 3 members of staff, I include myself because I found out 5 minutes ago that they just promoted me to a lecture. Thanks very much. So yeah. Very sweet of you, thank you. We have interests in quantum field theory, in high energy physics, high intensity physics, especially in quantum and non-perturbative effects. And we're very interested in all kinds of processes which occur in laser fields, such as pair production, vacuum birefringence, cascades, and I'll introduce these ideas as we go along. What I want to do today is give you a fairly easygoing introduction to some aspects of fundamental physics and laser fields. I've tried to aim this presentation mostly at the PhD students and postdocs without going into too many technical details. So let's just start off by thinking about the parameter region that we're going to be working in. So when talking about fundamental physics, we're used to thinking about high energy accelerators like the LHC and going to ever higher energies to access new physics. So there's a graph with energy on the vertical scale. And at the LHC, for example, you collide very high energy particles, but relatively few particles together, and you see what happens. So if we plot energy versus intensity, then the accelerator regime is over there. And the laser regime, well, that's a bit different. If you think about laser physics, certainly optical lasers, the energy of a photon in an optical laser is around about 1 eV. It's quite low energy. But in a modern laser pulse, there are maybe 10 to the 20 photons being delivered to a spot size measured in micrometers over a femtosecond duration. And this gives you a very high intensity. So laser physics is this regime down here. And the point is that there's not just interesting physics as you go up there, there's also interesting physics as you go across there. One of the candidate processes is the Schwinger effect, which we'll come to later on. But yeah, so we're thinking about going in this direction, increasing intensity and typically low energy. Of course, we can explore this regime by combining intense lasers with high energy particles and high energy photons. And this is kind of where my interests lie. So, here's an outline of the talk. Start off with classical physics and laser backgrounds. We'll look at what we mean by intense fields or strong fields, look at the relevant scales, and we'll look at an example. Then we'll turn to quantum effects and do the same thing. We'll look at when quantum effects become important, and then we'll go through a couple of examples, one of which is somewhat applied in the sense that I'm going to focus on using quantum effects to generate a GeV photon source for use in science. And the second example will be vacuum birefringence. This is more theory-orientated. Okay, so let's start with classical physics. What do we mean when we talk about a strong laser field? Well, let's suppose our laser has some typical electric field strength E and frequency omega. And we put a particle into this field and we ask, how does it move? Well, it moves according to the Lorentz force equation, right? Here it is. X is the particle position, a dot is a derivative with respect to proper time. There's the laser field strength, electron charge, electron mass. Let's take this equation and make it dimensionless. So I measure time in units of the inverse laser frequency. That's the natural scale. Then the Lorentz force equation looks roughly like this. Okay? And you've got this dimensionless coupling parameter here, which describes the strength of the interaction between the particle and the laser field. It's called A0, the dimensionless intensity parameter. So it's charge of a mass, field strength over frequency. Or if you want, charge of a mass, field strength times laser wavelength. What does it mean? What does this have to do with the field being strong? Well, if you put A0 equals 1 and stare at this expression, then A0 being equal to 1 says that the work done by the laser over a laser wavelength is the electron rest mass. So over a single cycle of your laser, an electron will be accelerated to relativistic velocities. Okay? So A naught larger than 1, relativistic physics. If you take the first expression here and stick in some factors of h bar, then A naught being equal to 1 is equivalent to saying that the work done by the laser over a Compton wavelength, so that's the natural kind of length scaling QED, if you like, is larger than the typical energy of the photons in the laser. So the A naught larger than 1 also corresponds to the regime of multi-photon effects. A naught is the coupling between the particle and the laser. A naught being larger than 1 means you can't do perturbation theory in A naught. So, the standard physicist's tool of attacking any problem whatsoever, perturbation theory, goes out the window. And you have to find other methods, other ways to tackle your problem. So, when I say a strong field or an intense field, I mean fields where A naught is larger than 1. Simple as that. What does that correspond to? Well, A naught can be written approximately as the laser intensity in units of 10 to the 18 watts per centimeter squared. Okay? This kind of intensity is regularly achieved in various facilities around the world. So we're definitely in the regime today of relativistic, nonlinear laser physics. Okay. Let's look a little bit more deeply into classical physics. In the box at the top is the entirety of classical physics. That's the Lorentz force equation, telling you that fields accelerate particles, again. And that's Maxwell's equations, telling you that particles are the sources of fields, okay? So, a field accelerates a particle, that particle radiates electromagnetic energy, right? Changes the field. And normally, and what we did in the previous slide, was that we actually neglect this arrow going backwards, right? We think that we have a laser field, we put an electron in it, and it moves around. We don't normally think of the fact that energy is being taken from that field to move the electron, as the electron must be radiating as well, so itself it's losing energy, which is correcting what we thought was the laser field we started with. And collectively we might call this radiation reaction or back reaction, and we normally neglect it. It's normally a small effect anyway, so fine. But let's think, when might radiation reaction become important? So we're asking, when do we have to go from just worrying about the Lorentz equation to worrying about this coupled system of actually highly nonlinear differential equations? Well, when might back reaction be important? To estimate that, we work out the energy radiated by an electron according to Lamour's formula. There it is, just the time integral of the acceleration squared, okay? And let's just equate that to electron rest mass. So we say back reaction is so important that the electron is losing all of its energy. Okay, it's a rough approximation, but it gives us the right answer. So let's estimate this guy. Once again, time we'll measure in units of 1 over the laser frequency. There it is. The acceleration we'll take from the Lorentz force equation. There it is. And we set all this equal to the mass. We can express that in terms of A naught, our intensity parameter. And the condition for back reaction to become important is just that the frequency over the mass, sorry, laser frequency over mass, times A naught squared is of order 1. If you plug in the numbers, this boils down to A naught being of order 100, this is for optical lasers, and an intensity of 10 to the 23 watts per centimeter squared. I think this number cropped up this morning, right? What this means is that at these kind of intensities, a little bit beyond what we can achieve now, you're in a really heavily nonlinear regime of classical physics. I should say that if I account for pulse length effects, the fact that there's many oscillations of the laser in a typical pulse, and also for relativistic effects, so I put the gamma factors back in, then this intensity will go down quite significantly. In fact, we can access this regime of radiation reaction even today. And there will be experimental results appearing this year on that. Okay, so what I want to show you now is just a little example of very high intensity classical physics. The point is just to show you that even classical physics in the high intensity regime still holds a few surprises. imagine that I have somehow created a very intense standing wave. So maybe I've fired two lasers across each other to set up a standing wave. Let's just ask the question, how will a particle move in that standing wave as I increase the intensity? Here's the answer. This is three separate pictures showing you particle motion in fields of ever-increasing intensity, order 100, 1,000, and 10,000. Yes, that is ridiculous, but bear with me. These are trajectories in space and space. The red dashed lines show you where the peak of the electric field is in space. The blue dashed lines show you where the peak of the magnetic field is in space. Okay, this is a standing wave, so that's where the electric field is maximum, and that is where it is minimum, if you like. So, A naught is of order 100. Remember from the previous slide, this is where we expect back reaction, radiation reaction, energy losses start becoming important. How do electrons move? So, here's an electron. It starts over near the peak of the electric field, and it follows this curve. It's accelerated by the field, it gets turned by the magnetic field, it loses energy, and it spirals in to the, let me get this right, to the node of the electric field, right? So if you imagine that the electric field is giving you a potential, then this particle is just rolling down the potential well, losing energy, and coming to rest in the bottom of the potential. Well, that makes sense. If we then increase the intensity so that back reaction and energy loss effects become even more significant, then the particle moves as so. It gets trapped in the, I always get this wrong way around, in the node of the electric field. It tries to escape, but it gets pulled back in. It's losing all of its energy all of the time. So as soon as this electric field tries to accelerate the particle, all of its energy just gets radiated away, and it gets trapped near the node of the electric field. Final picture. We go to ridiculously high intensities, and something very strange happens. Now I start a particle off at the bottom of the potential hill. So in the peak of the magnetic field or the node of the electric field. This particle gets accelerated. It starts moving parallel to the electric field. It's a very complicated, intricate motion. But in general, what happens is that it migrates across to the peak of the electric field. So it rolls back up the potential hill. And then it oscillates around the peak of the electric field, okay, at the top of the hill. So what you traditionally think of as an unstable position of equilibrium has become a position of stable equilibrium at very high intensities. This is very counterintuitive behavior, and it's rather complicated due to the interplay of extremely violent accelerations from this very high intensity and extremely hard, abrupt energy losses from back reaction and radiation reaction. This phenomenon is called anomalous radiative trapping because it is anomalous, it's a bit strange, and it traps particles where you don't expect them to be, at the peaks of the electric field. It's the same picture again. This is just a wavelength of the standing wave. This is increasing intensity, A0, and the color just shows you density of particles. And there are many interesting effects regarding trapping and focusing of particles. In standing waves, it's fundamentally a chaotic system. Anomalous radiative trapping lives up here at the top. You see these very dense black areas. This means the particles are being concentrated there. And if you just look down the page, there it is. It's at the peak of the electric field. Okay, so even classical physics can be a little bit surprising at high intensities. Now, yes? Well, it loses all of its kinetic energy. So it's basically, so it accelerated very hard here, and then it's brought almost to a stop. And then it's accelerated hard again, and brought almost to a stop. Yeah. So each of these kicks, if you like, is one cycle of the laser. So it's moving up and down like this, in this regime, which will be important later on. Oh yeah, so good, thanks for that question. Remember this kind of motion, it's gonna be important later. So this electron is oscillating up and down the electric field like this. Yes, so classical physics at high intensities. Well, you might be thinking, at such high intensities, surely quantum effects are gonna kick in, right? and this all just goes out the window, destroyed by quantum effects. Well, fortunately not. I've cheated slightly, and I've shown you the quantum calculation. The classical calculation is that one, okay? No difference down here, low intensities, no difference down here, low intensities. Up here, okay, in the classical prediction, you see the same trapping phenomena. It's just that they're much more well-defined here, okay? So the particles are trapped in very, very tight areas, and all that happens when you go to the quantum case is that these results are smeared out. Okay? So this is an example where the effect that you're interested in, this anomalous radiated trapping, actually survives the classical to quantum transition. If it hadn't been, I wouldn't have shown it. Okay, so now that we've started talking about quantum effects, let's turn to quantum effects. Play the same game again. When are quantum effects going to become important? Well, let's start by asking, what kind of fields do we associate with quantum effects? What field strength do we associate with quantum effects? Well, you can take the fundamental constants, h bar and E and C and M, and put them together and arrive at an electric field strength called the Schwinger field. Here's another way of deriving it. You ask what happens when the field is so strong that the work done by that field over a Compton wavelength, fundamental quantum scale, is equal to the electron rest mass. So that's the work done by the laser there over a Compton wavelength, that's that guy, is equal to the electron rest mass. And at such a field strength, the laser becomes powerful to, if you like, pull virtual pairs out of the vacuum and put them on shell, and make them real. So it's at this field strength that you get spontaneous creation of electron and positron pairs. Okay? This is kind of the cutoff for laser physics. Because if you focus your laser and achieve fields beyond this strength, the photons in your laser will just turn into electrons and positrons. And the value of this critical field, Schwinger field, is about 1.3 times 10 to the 18 volts per meter. That's very high, okay? Which makes this process very hard to see in an experiment. But how does that relate to the scales at which quantum effects set in? Does this mean that quantum effects are only important at 10 to the 18 volts per meter, which frankly lies a long way in the future? No. What have I neglected in this equation? Okay. There are no gamma factors here. Okay. Neglected relativistic effects. Let's see. I want a parameter which describes quantum effects, takes account of relativistic effects. It's going to depend on the electric field strength. It's going to have to depend on the gamma factor of the particle, to be relativistic. If I multiply the electric field with gamma, I don't get something dimensionless. So I divide by the Schwinger field, and I get this parameter chi. This guy is called the quantum efficiency parameter. It tells you when quantum effects are important. It's just your laser field strength divided by the Schwinger field times your electron gamma factor. And of course, there are nice ways of writing this which make it look manifestly covariant and so on. But that's not important today. In terms of the intensity parameter A0, this is, again, for an optical laser, 2 times 10 to the minus 6 times A0 times gamma. So you can see that you can make quantum effects important, make chi larger, either by increasing the intensity, or by increasing gamma, or both. And the kind of literature standard line is that quantum effects become important for chi of order 1. Okay, just like relativistic effects became important for A0 of order 1. What kind of effects are they? Well, excuse me. Chi of order 1, you get various kinds of pair production effects. So stimulated pair production, if you fire a high energy photon into your laser, you'll create pairs. Feynman diagram. You get cascades. Above 10 to the 23, 10 to the 24 watts per centimeter squared, depending on which paper you read. Any particle presence or photon presence in a very intense laser will lead to an avalanche of particle production. Even having an impure vacuum will lead to an avalanche of particle production. Because whatever is in the field of the laser will be violently accelerated. It will emit high energy photons. Those photons will create electron-positron pairs. They'll emit photons, they'll create pairs, and you get a cascade or an air shower of particle creation. You might think, ooh, that's exciting. That'd be nice to see. Yeah, it would. But as we're going to see shortly, it also spoils things a little bit. If you're creating masses and masses of particles, where's the energy coming from? Well, it's coming from the laser, and you're going to end up depleting your laser very severely. Okay? The cascades, while they are kind of a fundamental prediction of QED, aren't particularly helpful if you actually want to do something with your very intense laser, because there's a risk that your vacuum's not good enough in your experimental chamber, and your laser's gone before you can use it for the task in hand. Finally, there's Schwinger pair production. Okay? Electric fields of 10 to the 18 volts per meter will spontaneously create electron-positron pairs. Yeah, okay. So, let's put what we've talked about so far together. Okay, we talked about this anomalous radiative trapping in the classical regime, and we've talked a bit about pair production and quantum effects. Let's put this together. Look at an example, look at an application of quantum effects, which is in generating a GeV photon source. What do I mean? Well, let's think about a low-intensity laser first. Take my low-intensity laser and I throw electrons at it. The electrons have some gamma factor, gamma. They will undergo Compton or Thompson scattering in the laser, and they'll emit photons at a typical frequency, which is upshifted by a factor 4 gamma squared relative to the laser frequency. Okay, so you put 1 eV photons in your laser, you hit it with 10,000, and you get a gamma factor of 10,000, and you get, whatever that is, a huge frequency coming out. Okay? So then you think, aha, can I use laser particle interactions as a method to generate a source of high energy, hopefully high flux photons? This might be a useful tool in, say, probing nuclear physics or quark nuclear physics. Well, this is where these cascades and back reaction effects come back to haunt us. So you can try colliding your electrons with high intensity lasers and hoping that you'll get an upshift of the emitted photon frequency. But what will happen is that if you get any high energy photons emitted, they'll just get eaten up by the laser and converted back into electrons and positrons. They'll emit and they'll get eaten up by the laser. And so you might generate high energy photons, but they won't escape your laser fields. They won't be useful for doing any other science, because they'll just get converted back into matter. Alternatively, this cascade can happen so quickly that your laser is depleted. You might get a few high energy photons coming out, but certainly not enough to call it a source, nothing to be useful, not enough to be useful. And then, of course, there are the energy losses implied by radiation reaction. Okay? You've sent your particles in with nice high energy. You sent your particles in with gamma. By the time they actually get into the hot part of the laser pulse, they've lost a lot of their energy. Your effective gamma goes down, and you don't get the kind of high energy photons coming out that you want. So people have looked at this. This has been a very popular topic over the past few years. But the consensus seems to be that the presence of cascades and energy losses limits the efficient production of photons by this mechanism, by laser matter interactions, to sub-GeV energies. Okay? Maybe you want sub-GeV energies, then you're fine. Maybe you want to go higher, do really kind of exotic quark nuclear physics with very high energy photons or something. Well, then you want a higher energy source. How do we do better? Well, there is a way of doing better. And this is blue skies thinking a little bit. First of all, you use optimal focusing, or as close to optimal focusing as you can of your laser energy. You can get pretty close to optimal focusing by using what's called a dipole configuration. It's just an array of 12 mirrors arranged in 2 belts in a particular way, such that for a given incoming laser power, you get the highest possible field strengths in your laser focus. Okay? It's like the inverse of dipole antenna radiation. So the light is focused down, radially polarized, focused into a point. You get very, very high field strengths. If you can do this with a total power of 10 petawatts, then you enter the regime of A.R.T, this anomalous radiative trapping. Okay, so what that means is we've got focused laser pulses with very, very high field strengths in the focus, and we're in the regime where particles are trapped around the peaks of the electric field. Yeah? So they're very energetic particles oscillating back and forth along the peak of the electric field. Because of the way the particles move in the A.R.T regime, remember, they kind of move up and down like this. They will essentially radiate in only one direction along the, in this case, the z-axis. So here, the red and the yellow represent the converging dipole fields. There's the hot spot in the center, and the blue just shows you GeV photons being emitted along the z direction. Okay, so yes, this is great. This sounds like what we want. High energy photons being emitted in pretty much one direction. Sounds like a gamma ray source to me. I am a theorist, so tell me if I'm wrong. But then you've got this problem of cascades, right? We've got high energy photons being emitted. We're going to start cascades, lose all our energy, and our source will deplete it, will vanish. Well, the way we get around that is by tuning the pulse duration such that you avoid the cascades, essentially. You let the cascade grow a little bit so that you've got lots of particles in your focus and they're all emitting, but you limit the pulse duration so the cascade can't grow so much that you get significant back reaction effects. And so you try and derive a condition on the laser pulse such that you have less than, say, 10% back reaction effects. Turns out that's quite hard. That's what is going on in the center of this dipole pulse. Here are the converging fields again on the outside, and in the middle you've got electrons and positrons and photons doing all kinds of crazy things. It's a very, very messy system. Nevertheless, you can derive a reasonably compact expression which relates your pulse duration, that's just pulse duration on the left-hand side, to the incoming laser power. This is power plotted against duration again. Here's a curve corresponding to this equation. Basically, if you choose your pulse duration such that you're on this side of the curve, then you can get, what do I want to say? You can get kind of prolonged photon generation without significant back reaction, and you have a candidate source. So for example, if you have a total power of 40 petawatt, you want your pulse duration to be less than, what is that, 25, 30 femtoseconds. If you arrange that, and this is the kind of photon spectral angular distribution that you get out. So these are photons of energy 2 and 3 GeV being emitted basically in the z direction, in the minus z direction. Okay? Very narrow angular spread. Take an example of peak power 40 petawatts. Plot here is quite messy. What have we got? Blue is the laser field amplitude as it varies in time, right? And red is the flux of high energy photons coming out of your system. So what happens? You start focusing this dipole wave, the laser field amplitude grows and grows and grows. You've got no high energy photons being emitted, and then suddenly, bang, you get this peak of high energy photons coming out. The numbers, and then it's gone. Okay, so this peak contains about 10 to the 9 photons in a well-collimated short duration beam with this peak brilliance, which is high. I'm a theorist. This number doesn't actually mean anything to me, but I'm told it's quite high. But the point is, this is the kind of behavior that you want from a photon source. In order to generate this, you do need to use this dipole configuration to get up to the maximum field intensities. Seems quite exotic. On the other hand, there are facilities like XCells in Russia, which are looking at 12 beam setups. So I think the message I want to take away from this part of the talk is that these quantum effects, like cascades, pair production, high energy kind of beam depletion and back reaction effects are not just there as a hindrance, but you can, in some sense, exploit them. You can use them in applications. Yeah. Yeah. No, no. Let's see. So, these dipole beams end up being radially polarized things. And the way they overlap, it's quite intricate and rather specific. So you have to have a particular distribution, a particular angular distribution at infinity, brought in a particular way, such that you get a non-zero electric field and a zero B field in the center. And you can't do this exactly because it needs 4-pi focusing. Right. With a dipole, you can get to about 90% of the optimum. As, you know, as the beams overlap, you're right. Some components cancel out, some reinforce, and there is there's old papers on optics letters which tell you basically there is a maximum that you can get to. I've forgotten the details, but I can give you the reference. Yeah. Yes. Yeah. Yeah. So the drop is understandable, right? Because the energy's gone into these guys. Let's see, 25. It's because the fields are still being pumped at this point, right? They're still being focused and coming in. It's just that, see? My understanding was this way, the remnant of the laser pulse coming in and being focused. And the fact and here, you're losing energy here still, but you're not losing significant energy to photons. Yeah. Yes. So now I see what you mean. Exactly. Yes. Sorry. Yeah. Okay. Okay. Let's move on. Okay. Second example. Vacuum birefringence. This was mentioned this morning. So vacuum birefringence is a purely quantum effect, and there are plans to measure this at a variety of upcoming facilities. So what is vacuum birefringence? Well, let me first remind you what birefringence is. Suppose I have some birefringent crystal sat on my lab desk. It's got a length L, and it's got refractive indices, n parallel and n perp. And I shine a ray of light through that birefringent crystal. The speed of the different polarization components of the light through the crystal depends on the polarization because of the refractive indices. And if you send in a linearly polarized beam of light, it will emerge with some slight elliptical polarization. That polarization ellipticity delta is given by pi times the difference of refractive indices, the length of your birefringent medium, your crystal, and then divided by lambda prime. This is the wavelength of your probe beam of light, right? So this is just classical optics. Okay. The quantum vacuum exposed to very intense light is also a birefringent medium. So what that means is that if I take my very intense laser and I just shine it on the vacuum, this fire laser, and I send in a probe photon or a probe beam of light through that intense focal spot, so it has linear polarization again, then the probe will emerge with a very small elliptical polarization, okay? Just as if it had passed through a birefringent crystal. This is a purely strong field effect, a purely quantum effect. What causes it? What causes it is this Feynman diagram. Okay? Light by light scattering. This just reminds us that in QED, it's possible for photons to scatter off each other if you fire them towards each other. It's not very often that you get photon-photon scattering, so the cross-section, even in part by particle physics standards, is tiny. And then you think, aha, if I was going to try and measure light by light scattering, then I would use a laser. Because even if the probability of the event is very small, you have huge numbers of photons in your beam, which increases the chances of seeing something. And these virtual electron-positron loops in the vacuum effectively conspire to generate refractive indices of the vacuum, just like a birefringent crystal has refractive indices. You can derive an expression for these indices using Euler-Heisenberg effective theory. This is just a low-energy effective theory of QED. To integrate it out all the fermions. All that's left is a Lagrangian describing classical Maxwell equations plus quantum corrections. Here's the Schwinger field appearing again. Alpha is just the fine structure constant, 1 over 137. From this effective action, you can derive an expression for the refractive indices of the vacuum. Given by 1, that's what we think of as vacuum, plus fine structure constant times a number, 7 or 4, depending on whether you're looking at n parallel or n perp. And then you have the square of your laser electric field strength over the Schwinger field. There's the expression for the ellipticity induced by birefringence. Take these refractive indices, plug it into this equation. That's what you get. So then the question is, can we measure this ellipticity induced by vacuum birefringence? Well, if we want to measure a signal, then we want to make it as big as possible, right? So how do we make this guy as big as possible? Well, the first term we can't do anything about. We can make this big by having very strong electric fields, and as we already mentioned, you do that using an optical laser, okay? So you generate your birefringent vacuum by using very intense fields with very strong electric fields. L is the interaction length. We'll come back to that. But you can make the final factor large by making lambda prime as small as possible. That's the probe wavelength. So you want probe frequency as large as possible. So then you say, okay, I will choose my probe to be an X-ray, and I will use this to probe an intense optical laser and try to measure vacuum birefringence. Just to hammer the point home, is the experimental setup. You have an X-ray or an X-ray laser with linear polarization, and you collide it with a very intense optical laser. To get the best signal, you also want that guy to have linear polarization. The X-ray beam will emerge from the interaction with a very, very small ellipticity. Pass this through a polarizer, and you measure, then of course you measure the ellipticity of the beam just by counting the number of photons which manage to get through the polarizer. As an estimate for how small or how large this ellipticity is, okay, here's our expression again. First factor, 2 alpha over 15, that's about 10 to the minus 3. Electric field strengths at upcoming laser facilities, optimistically 10 to the minus 3 of the Schwinger field, maybe, a bit less. So let's say that factor is 10 to the minus 7. The interaction volume, or length, roughly the Rayleigh length of your laser pulse, 10 microns. And lambda prime, the wavelength of the X-ray probe, roughly 0.1 nanometers for X-rays. Put it all together, 10 to the minus 5. To generate this E over ES, I'm assuming a laser of 10 to 22 watts per meter squared at least. Okay, so an ellipticity in an X-ray beam of 10 to the minus 5. This is at the edge of what we could possibly measure with current technology. Huge leaps are being made in this in this area, specifically by the guys in Jena. So to measure vacuum birefringence, you would need very, very accurate X-ray polarimetry. Now, if it's a precision experiment, everything has to be accounted for very carefully. But this expression that we just derived, that we just saw, comes from Euler-Heisenberg, that was derived assuming that the field was just a constant field, right? A completely flat, homogeneous, constant electric field, which seems like a rather crude model of a laser pulse, which we know is focused in space and pulsed in time. So the idea of a precision experiment doesn't mesh very well with this very rough calculation of the refractive indices. So let's look at the influence of laser pulse shape on vacuum birefringence and on this ellipticity. So here are figures illustrating 3 different models of a laser field. That's the constant field, okay? It's just the same in all space and time directions. Here's a Gaussian beam, so it's focused in space, but it just oscillates forever in time. And here's a Gaussian pulse, so it's focused in space and it's pulsed in time. So we're increasing the level of realism as we go from left to right. All we're going to do is calculate the ellipticity in each of these 3 models and then compare it to some numbers suitable to upcoming facilities. So there's the expression you've already seen. Numerical factor, E squared over E Schwinger squared, the wavelength of the probe, and we set the interaction length to be twice the Rayleigh length of laser, okay? We have to put this in by hand for this case. Okay, so if then you redo the calculation with a Gaussian beam, you get a very similar expression. All that happens is you add a factor of pi by 4. Fine, that's easy. And then you do the calculation again, this time with a laser pulse. And you get some numerical factor, and then a factor of the pulse length over the Rayleigh length. Okay, fine. What does that mean? What does that imply? Well, let's take some numbers and plug them in. There are plans to measure vacuum birefringence at the High-BEF facility in Hamburg. Let's see. Yeah, so their laser has a total energy of 30 joules, wavelength 800 nanometers, pulse duration 30 femtoseconds. From these parameters, you can work out what Z naught is. Lambda prime is about 0.1 nanometer. Take these numbers and plug them in. And for the constant field case, you get 2.2 times 10 to the minus 5. Okay? Well, that's right. We estimated on the previous slide that it was going to be 10 to the minus 5. That's okay. So this is, at the edge of what could possibly be measured. Then you account for spatial pulse shape. And you get this factor of pi by 4, which reduces the ellipticity a little bit. And then you account for pulse length, and you get this factor. And you lose an order of magnitude. So by accounting for realistic pulse geometry, you lose an order of magnitude in your signal. And what I haven't told you is that the experimental signal is actually proportional to delta squared. So you lose a lot. This is certainly beyond what can be measured today, but let's be optimistic, only a little bit beyond. And there are definite plans afoot to measure vacuum birefringence, both at High-BEF in Germany and at Eli NP in Romania. High-BEF want to use X-rays, and they are focusing on developing very accurate X-ray polarimetry in order to be able to do this. At Eli NP, the plan is to use gamma rays as the probe. Now, if I just go back, so gamma rays, this becomes tiny. So you get a massive signal enhancement from this factor. The problem is that you then have to measure the polarization or the helicity flip, quantum mechanically, of gamma rays, which is entirely different challenge. So either way, challenging experiments, but very exciting, because an observation of vacuum birefringence would be an observation of light-by-light scattering with entirely real photons. That's never been seen before. This is an area where laser physics can literally, sorry for the pun, shine a light on a corner of the standard model that we can't investigate otherwise. Okay, on that note, I'll conclude. So, intense laser fields are a very promising, exciting tool for studying fundamental physics. There are new facilities upcoming with the aims of doing these experiments like vacuum birefringence, Eli, High-BEF, Vulcan, 20 petawatts in the UK. It's an exciting area for theorists because intense laser physics overlaps, contains, you have to take account of relativistic effects, collective plasma effects, quantum effects, and there's overlap with optics, plasma physics, particle physics, high energy physics, mathematics. And as I've only just touched on, of course, there are many applications of intense laser fields. So the example we looked at was exploiting quantum effects to generate a GeV photon source. Finally, there are many things that I haven't talked about today. I haven't said anything about physics beyond the standard model. Lasers can also be useful there. I also haven't told you anything about how we actually do calculations. Right? So there's a pile of literature on how you do calculations, either analytically or numerically. For more theory, I just want to promote the talks of the other postdocs, Adam and Daniel and Sam. I think we're all talking tomorrow on Wednesday. I'm here all week. Please feel free to ask me questions if you see me. Thank you very much for your attention.
Thank you, Anton.
The electron hole pairs that are made, what is the effect of the positrons on the light?
In which example, sorry?
Positrons are made, right?
Are made.
When you break down.
Yeah, yes.
What is the effect of the positrons on the whole cascade?
Exactly the same as the electrons. Where's the cascade? There it is. No, no, I don't think there's a special effect of the positrons. In these situations, they just behave like electrons with the wrong sign. They get accelerated and they take away energy and they emit.
Are there any plans to generate harmonics of these high intensity frequencies and then get closer to h bar omega of order MC square?
The honest answer is I don't know. I'm too far from experiment to be able to answer that question. Yeah, I was. So in terms of this diagram at the beginning, up here, the way I think about accessing this corner is by starting with very high energy particles in a very intense field. Okay, well then you could, so you would do Compton backscattering from a low intensity laser to generate your high energy photons and feed them into a second stage or multi-stage it. Perhaps the Eli representatives will know more about harmonic generation experiments.
Anton, couple of questions and a comment. I mean, there's the experiment by Burke. He did it with the slack beam. So what's the difference between his work and what you call pure photon-photon scattering?
So photon-photon scattering is loop.
Is
a loop process.
Yes. That was, I mean, he used the gamma rays from the Compton backscatter of.
Yeah, so that's
so these gamma.
Flack E144, right?
Pardon?
Flack E144.
That's right. That's something. Yeah.
So let me grab some chalk. So that's Slack E144, right? You send an electron in.
Yes.
Here's your background laser field. That's a terrible picture. You generate high energy photons and they create a pair.
Right.
Right? Tree level process.
Yes. No, I get it now.
Whereas what we're thinking about is.
That's right. Yes.
Is loops. Yeah. So,
this
guy has a. This guy doesn't have a classical limit because it's pair production.
Yes.
But it's semi-classical. This guy is not.
Yes. The other question was, I mean, you didn't mention photon splitting because you do that work as well. When does that come in? Is that a lower threshold or a higher threshold?
in magnetic fields, I think it comes in around the same time.
Uh-huh.
Lasers, I'm not so sure, actually.
Because
Yeah.
I mean, you've got that showing a limit with magnetic fields as well, which is about 10 to the 13 Gauss or something. I mean, it's the field strength of a neutron star, isn't it?
Absolutely. We don't often look at photon splitting.
Yeah.
I've forgotten the reason why.
And the other question, final question, we can chat about this later. The final one would be the unreal radiation question.
Oh.
Now, this is always is it, can you actually see it? Is it in, our frame, or is it in
You can't put me on the spot and ask me to put my foot in one camp or the other. Is unreal radiation?
Well, no, you can, I mean, that's fine. I don't think anyone's really clear, even maybe unreal.
My gut feeling is that the Russian camp probably are right on this. So it's just multi-photon Compton scattering. In which case, yeah, you can see it, but, well, it comes down to a question of how you interpret it, I guess. Yeah, that's tricky. If you could get it past the Nobel committee, of course. Depends very much who's on that committee. You populate it with the wrong camp, it's not getting through.
Can I ask a question? Yeah. I'm mightily impressed by the anomalous radiation trapping.
I sense there's a but coming, Tony.
Hey?
I sense there's a but coming.
No, there's no but.
Hooray.
No. Unless you think this is a but. But I'm wondering how robust it is. Right. When you do it all self-consistently. I mean, you showed some simulations. I mean, were they fully self-consistent in which the EM fields were?
Yeah, so let me see. So this guy is just standing wave background with radiation reaction, but no pair production.
Right.
So this is not fully consistent because you're going to get pairs. However, the simulations at the end for the GeV source, that's everything.
So that was a bit code,
That was that.
QED stuff and everything? And
So this guy, I mean, this is really from the simulation we did to get these results. So fully 3D pick.
Which code was that?
Picador. Brilliant. Yeah.
So another question about the radiative trapping. In this other plot you showed at the beginning, in the quantum case, it looked a bit like right, you have something like bifurcations there of the density distributions. It looks a bit like, yeah. Is this something?
It looks like bifurcations. I don't think it is. There's no multi-valued stuff going on here or anything. I think it's just a combination of how we plotted it in the resolution. These thin lines are, it's hard to compare because these thin black lines should be very, very black. So here, all the particles lie in very, very narrow regions of space. And it's hard to get that impression across with the resolution. But then these lines just get broadened out to these edges.
Did you see pair production for chi values less than 1 even?
So pair production is there for chi less than 1, but it's exponentially suppressed. So if we look at this process, you fire a high energy photon into your laser, it turns into pairs. That becomes probable at around about chi equals 1. For chi less than 1, so quantum corrections to Thomson and Compton scattering, there you can see those for chi beginning at 0.1, 0.01 even.
Like, does it also depend on how long a particular particle keeps on interacting with the laser?
Yes, absolutely. So again, this is the most basic estimate for what measures quantum effect. You should take account of pulse length as well.
And the second question was, what was the density of the electrons that you used when in the laser, in the interaction with the laser? In your coming plots that you showed.
Which part, sorry?
The plot where you showed the beam depletion, the density of the electrons. Sorry, I wasn't.
Here.
Yeah, here.
So here we started with a what was the density? I don't remember, but in sorry. This formula, more generally, also contains the the starting electron density. Here it's been set to some value, so I can't see it. I can't remember what it is.
Because what I think for like very low densities sometimes means I'm not sure, but the radiation reaction also may not be important.
No, so the density definitely does play a role here.
Yeah.
Absolutely. Yeah.
Okay. Now the third and final question.
Yeah.
Sorry. When you calculated about the vacuum birefringence, the delta, the phase difference factor, I was interested in knowing that is this delta can be used to estimate the Stokes parameters also?
Yep.
So you like just do the cos delta and sine delta gives you the third and the fourth Stokes parameter?
Yeah. So if you if you say that your probe beam is is monochromatic X-ray pulse coming in, then all the calculations look exactly like they would for in classical optics. So the refractive indices behave the same way, the Stokes parameters behave the same way, everything.
Because why I'm asking this is because for a monochromatic wave, if you have a delta, the Stokes parameter is quite easy. But for like a polychromatic, you need to go to calculate the coherency matrix because that's what is additive. Your Stokes parameter cannot be directly added.
No, so I mean, I think once you go beyond monochromatic, personally, I don't really see the use of Stokes parameters so clearly. But I mean, if you have a certain game that you play with non-monochromatic waves, classically, then you'll be able to include these indices in a very natural way. Yeah.
Because I tried doing that and I lost the phase factor in such kind of measurement.
Okay. Yeah.
Because in general, if you have radiation, you get both the real and the complex.
That's right. Yeah.
Here you don't have the complex.
Let's see. I can point you to paper, at our paper where we do with everything with the indices and the waves, and we have the real and imaginary parts and the phases.
Okay, that will be great. That will be great. Yeah. Okay, thanks.
So the plot where you explain the particle dynamics in the standing wave with the two counter-propagating waves. So where when high naught, it's sort of going up the hill.
Yeah.
So is it possible to explain something with like a equivalent Fermi-like acceleration where its particle is bouncing back as you are increasing A naught means the number of photons are increasing. So basically it's getting stochastically.
It's not a stochastic effect. He said, immediately changing his mind. I don't think it's a stochastic effect. So what we did to explain this motion is basically divide the laser, the standing wave up into different behaviors. So the electric field is rising, magnetic field is falling, et cetera, et cetera. And you have to analyze how the particle is going to move in each of these cases and then piece it together. I mean, I would love to be able to give you a really simple analytic model which explains this behavior, but I can't. We don't have one. Not a complete analytic model which works for all intensities, unfortunately. It's just that it's for these regimes, you can see from this kind of behavior that it's ridiculously nonlinear and complicated. Yes, I was thinking about this. You've got these kind of negative friction hills where things do roll up, stuff like this. That would be an analogy. I don't know how close the analogy would be, unfortunately. It's worth going back and looking at it. So for this case, you can actually make, there's a nice paper by John Kirk from last year, where he kind of has a semi-analytic model for this regime. It would be nice to do the same for this. Yeah.
This is truly getting to be a workshop now. I see Dino is doing a lot of work, going up and down with all these questions. And actually, this is truly out of the world for, of course, it's far beyond the present experimental domain, but we can think about all these things. You know the cavity QED, which is done for atoms, small cavities, with normal lasers. And that's how lasers have been doing tabletop QED for a long time in terms of cavity, measuring the fine parameters of atoms inside cavities and so on. Can we do the same? You know, you're saying that 10 to the 23 is where things start becoming possible, radiation reaction and stuff. Suppose you have this field inside a cavity, then you can just boost up. But the problem is that the cavity will have its own preferred spectrum. Yeah. Right? And so, has anyone thought of what happens when you notionally think of these things inside a cavity?
High intensity cavity.
High intensities inside a cavity, even higher intensities. And you can write theoretically you can consider, there's no harm.
Absolutely.
Whether we'll really do them or not, I have no idea.
Yeah, whether you'll blow your chamber apart or not. I can't think of any papers that have considered it. Maybe someone in the audience does. No?
I just like
invented a subject. Well done.
Yeah, how it might change, because now there'll be these levels that you have to consider. Which the quantum optics guys call it as actually as a colored vacuum, because now the cavity chooses its frequencies.
Yeah. Okay. Yeah.
And you can suppress spontaneous emission. You can enhance it. This is all last 25, 30-year-old this kind of stuff. And so that's one thing that sort of is probably worth thinking about. This.
Yeah.
I know, but you never know. Yeah, but he's talking of standing waves already here, which is happening naturally because of this. So, exactly, yeah. But the cavity needn't be such a big one. It can be even a small enclosed volume where there's a lot of feedback, right? And the second thing is, as an experimentalist, how do I, even normal PICs are difficult for us to figure out. We just take it as the theoretical query gives us, saying this is simulation, this is the result, does it match your experimental? What is a quantum simulation? I mean, what's your cell size? What's your, how do you do this?
So I do things with a pen and paper.
But suppose somebody has to do a simulation.
Someone has to do a simulation, absolutely.
What does he do? Does he go to the de Broglie wavelength and then take?
No.
What would be a cell size? Are there something as quantum PICs?
Are there something as quantum
particle in cell simulation?
No, not fully quantum, no. So when we do extended PIC simulations, it's not like doing lattice QCD, where you have a discretization of the theory with some cell size or box size.
Okay.
It's classical PIC in which you mock up quantum effects.
So you're just throwing them in?
Yeah, exactly. You put them in as like interaction operators on the right-hand side of your equation, essentially.
You do all this is analytical stuff that you
No. So I like doing analytics. So this has been a real mixture of analytics. So the birefringence stuff is all analytic. Okay. The cascade stuff is almost entirely PIC, but of course we have to derive, so these kind of expressions we have to derive analytically using various estimates and what have you. And in the regime of high intensity, the approach which is currently used, the classical PIC plus quantum extensions, should work. Okay, there's lots of old arguments by very powerful Russian groups which say this will work because blah. Well, actually, in the where you can test it analytically, it does seem to work. There are boundaries for PIC codes. They're not a cure-all. For low intensities, they get quantum effects completely wrong. There's questions about whether or not they consistently include beam depletion effects.
Okay. Thank you.
This is a workshop now. This is a crazy question.
It's all on me, yeah.
You mentioned beyond the standard model, actually. I mean, what are the things that you think are beyond the standard model? Would that be getting close to Planck scale physics or beyond the gut scale or what? I mean, I don't think we've got... No, just with anything. Just with anything.
Anything. Oh, what's beyond the standard model? I don't know. I don't think it's string theory. Did I? I think that must be something else. I don't think I mentioned quantum gravity. I don't know, but what I will say, for the benefit of the audience, is that there is lots of nice theory you can play with laser physics and then going beyond the standard model. So if you know anything about doing calculations in strong fields, the way we do it is by assuming typically that the laser is a plane wave, and then we use Volkov solutions. And then this whole setup of Volkov solutions and strong field QED, it turns out is really, really closely related to something called very special relativity, which is a beyond the standard model theory of physics. It's purely a kind of a theoretical construct or theoretical mapping, but there's lots of nice games you can play there. So there are things you can explore with this area. But going back to your question, do I know what's beyond the standard model? No, I don't. I don't think it's supersymmetry. I think that we have controversial. I think there's probably some really deep, interesting mathematics to do with gauge theories and Yang mills that we just don't understand yet. I mean, there are aspects of QED that we don't understand yet, frankly. No one ever talks about this when you're going on about string theory and what have you, but there's still a lot of quantum field theory that we don't. Yeah. Why? Academia these days. Well, they shouldn't be, but on the other hand, if they want jobs and they want to get funding, then I know. Now I'm going to do crazy stuff for the rest of my life. I'm going to go back to strings. Yeah. I'm not.
When you have already put, when you already put standing waves of a particular frequencies, is it not like cavity effect already?
Is it not like?
In your framework, you already have a standing wave, and the frequencies are already limited. I mean, you're only choosing certain frequencies.
Yeah.
Is it already like cavity, or do you have to put anything else?
Is it like a cavity? Well, so here in this example, you're right, the frequencies were chosen, and these waves extend infinitely in all directions. It's a bit like a cavity, if you like, but a very, very big one. Yeah. Yeah.
I guess if you're going to test this experimentally, you're going to have to focus a beam, two beams. So you're going to have to include non-plane wave types.
Oh, yeah, yeah. So, no, I should say that this is not plane wave.
It's not plane wave.
So, okay, this picture is not. Okay. This is actually in the dipole configuration, so the radially polarized guy. Okay. And the calculations for the Jeb source, that's all
3D, yeah.
That's all 3D dipole focusing. Yeah. So I only use plane waves and I can definitely get away with it.
Okay, I guess one may number.
Sorry, I was just wondering what models Picador uses for the quantum effects, to simulate quantum effects.
Picador uses, for the most part, the same quantum routines as the PIC codes, but with a variety of improvements to take care of soft photon, infrared issues, and also to take better account of cascading it. So your computational time grows humongously when you've got lots of particles, and there are lots of new routines in there dealing with exactly this problem. So that you can keep everything, in your simulation and everything stays inside the cell walls and whatnot. Is it completely stochastic? No, it's completely stochastic. So there's no double counting. So the propagation is Lorentz, but done consistently using classical PIC, and then quantum takes care of everything else. So no Landau-Lifshitz, no Sokolov, or anything like that.
Well, I guess no more questions. If not, let's thank Anton.